If you were ever going to understand one thing about scuba diving, it should probably be these two laws of physics, Boyle's law and Dalton's law, because they govern every single scuba dive we conduct. So let's explain them simply in today's episode of Scuba Science. Don't worry, this is not some kind of high school physics. This is more like the please don't kill me underwater type of physics. Every scuba diver should understand this, and realistically speaking, when you get scuba certified, regardless of which agency you train with, you are probably learning this in one of the very first chapters of theory. By the end of this video, you will understand how depth, pressure, volume, and density are related to one another, why and how airspaces shrink on scuba dives, and why some gases get more dangerous with depth. Boyle's law is all about the relationship between depth, pressure, volume, and density. Simply put, the deeper we scuba dive, the more the pressure increases. To put it very concretely, using the metric system, which is a very easy and clear way to understand, here at the surface we experience 1 bar or 1 atmosphere of pressure caused by the atmosphere. For every 10 meters we dive underwater in seawater, we experience an additional 1 bar or 1 atmosphere of pressure. That means that when we dive down to 10 meters, we will experience a total pressure of 2 bars. The one from the atmosphere plus the one caused by the 10 meters of seawater. When we dive to 20 meters, this becomes 3 bars of pressure, 30 meters, 4 bars, and so forth. Of course, as the pressure increases, any gas-filled volume would logically shrink because the pressure on it increases. This is in fact linear, so as we have a volume that has a total volume of 1 at the surface, we take that down to 10 meters where the pressure is 2 atmospheres, the volume will have a volume of 1 over 2. As we go down to 20 meters, this volume will shrink to 1 over 3 or a third. We go down to 30 meters, the volume will shrink to a fourth. Of course, as the pressure increases with depth and volumes shrink, logically, the gas in that volume becomes denser by the same factor. So if we dive down to 10 meters, the density of the gas in our lungs increases with a factor of 2. As we dive to 20 meters, this becomes 3x, 30 meters, 4x, and so forth. So this is a very linear relationship across the board. Why is this important? Well, when we scuba dive, we are of course exposing some air volumes to this pressure change and therefore to this volume and density change. Not in the least our lungs, which are inside our body and filled with gas. As we dive down, our lungs don't really shrink so long as we don't hold our breath. We simply keep breathing and keep inhaling ever denser air as we descend. So when we dive down at, let's say, 20 meters depth, we are in fact experiencing 3 bars of pressure. Our lungs will still expand to the exact same size as always, as long as we keep breathing, but the density of the gas inside our lungs will be 3 times higher. And this is important for understanding Dalton's law, which we will talk about in a minute. We of course also have air spaces on our body, such as for instance the gas in our mask, the gas in our BCD, and if you're wearing a dry suit, the gas in your dry suit. As we go down, it's very important to equalize these air spaces as well. While we equalize our lungs automatically by simply breathing continuously, the mask has to be equalized by exhaling into it from the nose. The BCD and/or dry suit have to be equalized by putting air into it from our scuba cylinder. These are all techniques you learn while taking scuba classes very early on. The same is true when we ascend. So when we are down at depth, let's say again for the sake of argument we are at 20 meters, 3 atmospheres, we have equalized all these air spaces in and on our body to 3 atmospheres. When we ascend, these gases will want to expand as the pressure on them starts to decrease as depth decreases. There as well, it is of course important to equalize these air spaces, or in other words, to let gas escape as we ascend. The biggest risk for not doing this is lung overexpansion injury. If we are at 20 meters, 3 atmospheres, our lungs are filled with air that is 3 times as dense and has the potential to expand 3 times as we ascend over these 3 atmospheres back to the surface. Luckily, equalizing our lungs on the way up is very easy. It is the same as equalizing them on the way down, namely just breathing continuously. But it is important to understand that if we were to hold our breath up on ascent, this expanding gas has nowhere to go and we would simply cause a lung overexpansion injury and rupture our lungs. So not holding our breath upon ascent, or really ever during a scuba dive, is really key here. Gas in our masks typically escapes by itself as we ascend, and gas in our BCD or dry suit has to be vented by the scuba diver as we ascend. Once again, these are the finer details of scuba diving that we learn during scuba diver training. Before we continue on to Dalton's law, I want to take 1 second to talk about Divevolk, as they are a proud supporter of the Dive Saga channel and SCUBA Science. Divevolk produces housings for smartphones, and if you do watch our episodes, you see that I actually use them regularly as well. They're great for taking quick pictures underwater, even shooting video. I even use them for watching videos during long decompression times, because in the back of the housing is a fully flexible screen that allows you to use the touch screen of your smartphone. It's super durable and fully waterproof, and you can actually use most features on your phone during the scuba dive. This is a great way to start practicing underwater photography and videography without breaking the bank and buying an underwater camera. So if you are interested in picking up a Divevolk housing, I'll put a link below. You actually get a discount on the product, and it does also support the Dive Saga channel and SCUBA Science. Dalton's law is all about partial pressure. It states that the total pressure of a gas mix is the sum of the pressure of the individual gases in that mix. Air, for instance, which we use when scuba diving, is not a singular gas. It actually consists of 21% oxygen, 78% nitrogen, and 1% of other gases. For the sake of simplicity in this video, I will simply assume 21% oxygen and 79% nitrogen. As we know from Boyle's law, we understand that there is 1 bar or 1 atmosphere of pressure here at the surface. That means that the air we are breathing has a total pressure of 1 bar. This total pressure of 1 bar is of course caused by the sum of the pressures of the oxygen and the nitrogen in the air. In other words, 0.21 bar of that 1 bar is caused by oxygen, 0.79 bar is caused by nitrogen. You add those two together, you get 1 bar of pressure. Now, if we think back to Boyle's law from earlier, we know that when we descend down to 10 meters, we have a total gas pressure of 2 bars or 2 atmospheres. That total pressure is caused by the sum of the oxygen and the nitrogen, which is now 0.42 bar for the oxygen and 1.58 bar for the nitrogen. Still 21% oxygen, still 79% nitrogen, but twice the effect of the gas. And this is a key word, effect. At the end of the day, Dalton's law is all about how these gases affect us as we go underwater. This is important to understand because, for instance, gas narcosis and specifically nitrogen narcosis can become an issue at depth. While the 79% nitrogen in air is perfectly safe at the surface and is not by any means narcotic, nitrogen does become narcotic under pressure. When we go down to a depth of 30 meters or 4 atmospheres, the total pressure of the nitrogen accounts for 3.16 bar of the total gas pressure in our lungs. This 3.16 bar is a very different game than the 0.79 bar of nitrogen at the surface, and can be narcotic. This is even more true for oxygen, which becomes toxic at a partial pressure of 1.6 bar. That means that if we have 0.21 bar in our 1 bar of air, oxygen could become toxic at 66 meters of depth. It is very important to take additional training before going to those depths. or before using gases with a higher oxygen content, where you might learn limits that are more conservative than what I'm talking about here, because of course as scuba divers we want to stay away from those limits. So by all means, this is not a replacement for scuba diver training. You should stick to the limits that you learn from your scuba instructor. If you're interested, you should check out our video about the gases of scuba diving. In that video, we talk about nitrox. Nitrox is a gas that has a higher oxygen content than regular air. We do this to reduce our decompression times, but a higher percentage of oxygen, of course, means that as we descend, we will reach this 1.6 bar partial pressure limit much sooner. So in other words, gases with a higher oxygen percentage will have a shallower depth limit before they become toxic. Once again, you learn this in nitrox training, so by all means, take those classes if you are interested. In conclusion, Boyle's law deals with the depth, pressure, volume and density relationships, whereas Dalton's law deals with partial pressures of gases. If you find this interesting, consider subscribing to the Dive Saga channel. You can even click the join button. This actually gives you access to extra videos, to the SCUBA Science scripts, and it supports the channel in a structural way. Also consider checking out our sponsor Divevolk if you want to get your own underwater housing for your smartphone. You can pick it up at a discount. I hope you enjoyed this episode. Boyle's law and Dalton's law are very good examples of how it is almost impossible to dive safely without scuba science.